Hello and welcome back to Calculus 3. Today's lecture is on cylindrical and spherical coordinates, so we're talking triple integrals. And I did mention these coordinates in the past. I said that they're going to build off of the polar coordinates, and if you don't understand polar coordinates, then clearly this will not be fun. So what we have now is a method to find volume of objects that are round. We are going to start with a very basic shape, which is just a pipe or a soda can or something, which is called a cylinder. And cylindrical coordinates are the coordinates that are meant to deal with those types of objects. At this point, I'm going to ask Kevin to take both of the objects he has in front of him, the egg and the thermos or whatever it's called, and show you the two objects. So these two objects will both be computed with cylindrical coordinates. Thank you. Right. So that's what we are going to do now. We are going to take a look at the cylinder. This cylinder will have the radius r and the height h, and I will understand that this height h is actually z, right? And r will give us the polar coordinates. So now, for cylindrical coordinates, let's say this one over here, I will have r theta z. So if I am in some kind of 3D environment, x, y, z, I can locate a point by, let's do red, going out r units, swinging that for theta angle, and then going straight up z units to give me a point that it's r theta z. So you see that the first part of you figuring out where this 3D coordinate is 100% polar coordinates of specify r, swing r, and then from that point go up or down, depending on z is positive or negative, and come up with a value. So conversion between the systems here should be clear. You have the set of equations that say x equals r cosine theta and y equals r sine theta and z equals z. Right? So this would be the set of equations which would change cylindrical coordinates into rectangular coordinates, because you can see that you have all of the r's and thetas given, and you are able to compute x, y, and z. On the other side, you have your good old r equals square root of x squared plus y squared. You have your theta, that it's inverse tangent of y over x, and finally z equals z as well. And this set of equations converts rectangular into cylindrical coordinates. Now we need to know these conversions because there will be cases where we have to switch integrals from rectangular to polar coordinates. So mainly that. The other way around, it's extremely rare. It can be done, but extremely rare. So what do we want to do now? Well, first I want to define the integral for volume in cylindrical coordinates. So volume is going to be given by the triple integral. I will put 1 inside, and then I'm going to have my regular string from, first we're going to have dz, and then I will have my regular string, which is r dr d theta. I hope you are already keeping this as a unit in your head. So this r dr d theta is a unit for integrating polar areas. And now I am multiplying the polar area base with the height z, making it into a volume. Does that compute for everyone? So this gives me the area, that's 2d, times dz, which is the height. Height times the area of the base gives me the volume. So this formula is sound. Now z will be functions in terms of r and theta. So over here I will go with let's say g and h. So g as a function of r and theta, and h as a function of r and theta. Now radius goes from a to b, and angles go from alpha to beta. Now we can also have radius to be a function. Now that would be a function of theta, and then you can introduce the flowers and hearts and everything else that we dealt with in terms of the polar coordinates. So this is the volume integral, and now I will use this integral to compute the volume of just the most basic soda can. All right? So what are the dimensions? Who's fast on the phone? Find the dimensions for a soda can. Just type in Google dimensions for soda can. We are going to calculate the thing. Thank you. So height of the soda can is 4.83 inches and diameter is 2.13 inches. Thank you. So now what am I going to do? Well, first off, I'm going to figure out the radius, which is 1 point and half of 13 is what? Very good. Right? So we have half of 13 is 6.5, right? And we have height at 4.83 inches. So when I draw my soda can over here, what do I see? I see there is a base, and that's my z equals 0. I see there is a top, and that's my z equals 4.83. Because it's a flat plane on the bottom, flat plane on the top. We're just working on the very simple calculation here. And we also have the radius. So now to find the volume of this, I will crank my triple integral. I have my dz r, dr, d theta, right? Z is going to go from 0 to 4.83. R is going from 0 to 1.065, and 0 to 2 pi on the outer integral because I want the entire soda can. Now you can, cut it in half, and then, you will have half of it and so on. So now this is equal to double integral 0, 0, 2 pi 1.065. Integral of z, so that will be 4.83 there, r, dr, d theta. Then we have integral 0 to 2 pi, integrate r, that will be r over 2, so 483 over 2 r squared, computed from 0 to 1.065, d theta. And now we compute all of this, so 0 to 2 pi. And let's use the Because this, since it's applied problem, so you clearly all by now switched to the phones, right? Stop. Throw the garbage away. R squared, so 1.065 squared times 4.83 divided by 2 is giving me 2.739 d theta. So all I need to do is to multiply this by 2 pi, and the final answer is 17.21 inches cubed. Now you can go and do your unit conversion. This is a perfect project question, right? Where I can ask you to actually take the soda can, take the measurements, use calculator to find the volume, and then do the unit conversion from inches cubed into the ounces and figure out if they're lying, right? On the volume. Because if they are, you don't have to go to school anymore, right? You're set. You are going into a 16-bedroom hacienda somewhere in, right? You're buying the island alone with that too, right? This is one. Right? Or you might be hired to, be a person who designs these kind of things. In this case, you're buying a house with 2 bedrooms in Frenchburg. You still have place to play. It's not that grim, all right? So there you go. So that's the cylindrical coordinates. Now, obviously, this is the most vanilla problem that you can think of, right? Because that's the cylinder. We want to see if we can hit some nicer examples that have more interesting situations. So let's go and find some examples from the textbook that we can solve, and then whatever examples they have in the book, right? You know all the letters and symbols and things. You can read those on your own. I hope you know all the letters and symbols, right? At this point, you're sitting in calculus class. It just takes so long. For the book to load. And this section has like 2,700 pages. And to scroll all of them, and I'm not sure why this website is not responding very well. It takes me a long time to get to where I want to be. This is terrible. Why is it taking so long? Come on. How are you? What's new? Calculus is new? No, calculus has been around 400 years now. It's nothing new there.
I'm just irritated that you took that Calc 1 project problem and did it in like 5 minutes.
Oh.
Yeah. The one with the Calculus?
That was last semester.
Or was it the Calc?
Yeah, the volume.
Yeah, it was Calc 2. It was Calc 2.
Of the pocket.
Mm-hmm. That's the power of mathematics. The more you know, the less work you get to do. You remember the problem where you had to integrate e to the x times sine x dx, and you had two integration by parts chained, right? And it took a page. We can do that in 3 steps without sines and e's and anything like that. It's amazing. It's just aha! There we go. So, oh my, come on, really, book? Where are the problems? They have a cylinder and a half a cylinder and a cone. Oh, there they are. You have to wait all the way to 29 to actually find stuff. Here's a very interesting problem. We can do either or. If you have a preference, we can do it. I mean, these are the spherical, so we're looking at these. You see a paraboloid over here that rests at the origin, and it's cut with a z-plane, z equals 25. Remember our ceiling is equals 10, right? So flat plane on top is equals 25, so it's just a cut. What is this? This is the umbrella, please. I'll say that, right? Not useful. Another one, right, looks more like umbrella. These two problems are the same. Now, this one looks bad and evil. This one doesn't look bad at all. Same thing. So, which one should we do as an example? The one on the bottom?
Yeah.
Because I see people going like this. Okay, fine. All right, so let's take a look at problem 31. So, I'm going to draw this real quick and then switch. All right, so this is what I have for the problem, and yep, that's that. So now we need to set up and find the volume of this object. So what should I do? Well, I'm going to start by first noticing that the object is round. And if the object is round, it's either going to be cylindrical coordinates or spherical coordinates. I do not have a part of a sphere here. Even though this looks like it's half a sphere or something, it's still paraboloid, okay? So, I mean, no, this is a sphere, but we can deal with it because when you take the square root on this side, it becomes z squared. Oh, no, it's not. It's not, because it would be minus z squared. So you would have x squared plus y squared minus z squared equals -4. So no, it's not a sphere. All right, so what do we do here? Well, we set up our integral. But first what I'm going to do is I'm going to shine the light from the top. When I shine the light from the top, it creates a shadow over here, and this shadow is the domain. So shine the light from the top, it creates the shadow on the bottom, and that shadow is the domain. And you know what that domain is? That domain is your r theta domain. And that domain gives you the limits for r and thetas. Great. triple integral of 1 dz r dr d theta. Don't forget this r. I am highly allergic. Now what do we have? Always remember that the inner limits, right, are for the top and the bottom bounds on the shape. The top bound, clearly square root of 29. Bottom bound is square root of 4 plus r squared. Very good. If you paid attention when I was giving you the formula, function g has to be in terms of r and theta. And then our conversion formula says that x squared plus y squared is equal to r squared. So what I am doing here is I am simply transforming this x squared plus y squared into r squared, and there we go. Now the next order of business is to figure out the domain. In order for me to do that, I need to know the equation of that circle. Otherwise, we are doomed. And we know that we can get that equation if we eliminate z's from our two equations. So to get the equation for the circle, right, for the domain, I need to take z equals root 29 and set that equal to z equals the square root of 4 plus x squared plus, well, just r squared. So now I have a square root of 29 is equal to square root of 4 plus r squared, from where r is clearly 5. Are we all Gucci with that? You have square both sides, kills the roots, move 4 to the other side, makes it r squared equals 25. And you drop negative 5 because distances are not negative. So there we go. My r limits are 0 to 5. And I have a full circle 0 to 2 pi. And now we have to compute this mess. So let me just one more time go through the entire argument and then we'll solve the integral. I have a shape that it's bounded by two z functions. The z function on top is the flat plane root 29. The bottom function is given by z equals this. Now, when you do your egg, right, it's going to be this function plus a different one on the top because egg has two different curvatures, right? So you trace that on a paper, you figure out. Your job is to figure this out actually for the project, for the egg that you will first boil and then play with, otherwise. I know, right? So I have a top and a bottom function, and it's always like that. That's easy, right? And now we need the domain, right? Your domain is dr, d theta, and need the domain limits. In order to get domain limits, you have to have the shadow of the domain. And the shadow of the domain. Now listen, for a stencil, there was a flower, right, punched into the dough. Well, you have the flower stencil, right? And that is r equals to, let's say, 3 sine 5 theta. Gives you 5 petals, flower. Well, that could be there, right, because if I have the stencil like that and I shine the light, that's what I see. I see the flower, which I know what the function is. So the goal is to find whatever that shadow is, and the way to do it is, well, you have equations that connect all of these things, you just need to set them equal to each other. Please remember, go back to your Calc 1, Calc 2 when we did integrals area between two functions. What did you do? You set the two functions equal to each other to find the intersection points, and those are your limits of integration a and b. This is the same thing. You are just going one dimension up. You are setting this z and the other z equal to each other to make the two-dimensional domain. Now, this two-dimensional domain in this case is a circle. X squared plus y squared equals 25. Right? Or, if you want to put it in the polar coordinates, is this plus theta goes from 0 to 2 pi for the full circle. And now all you do is you just plow through these calculations to Compute this, so that's going to be 0, 0, 2 pi, and 5. Square root of 29 minus square root of 4 plus r squared. All of this times r, the theta. And now you plug this in Mathematica and just get the answer. No, I'm serious. So now we're going to waste half of our life on doing this by hand. So integral of root 29 r is root 29 over 2 r squared. Minus, and the second one is, exactly, it's u sub. So now you go on the side and try not to do anything special. du equals 2r dr. So I need a 2, so that's a 1/2 of this. So it's 1/2 from the integral, and then I'm integrating square root of u, so that's going to be 4 plus r squared raised to the 3/2 times 2/3. Now these die, and then I still have d theta at the end. Don't forget these parentheses. Great. Nice. All right, and I need to calculate 0 and 5. So now we plug those guys in, and for 0, everything will... no, it will not die. So for 5, I have a 25 root 29 divided by 2. So 25 square root of 29. Minus, when I plug in 5 over here, I get 29, so it's going to be square root of 29 cubed over 3. When I plug in 0, first one dies, but when I plug in 0 on the second one, it doesn't, so it's a plus 4 to the 3/2 divided by 3. And all of this needs to be equal to, sorry, all of this is d theta, because we still haven't done that integral. Now, I can simplify. The square root of 4 is 2, and then 2 cubed is 8, so the last term is 8/3. So integral of 25 square root of 29 over 2 minus square root of 29 cubed over 3 plus 8/3. And you know what? All of this stuff over here has no variables, it's a constant. So who cares? You just get to integrate, you get the theta. So the answer is 2 pi, open parenthesis, 25 square root of 29 over 2 minus square root of 29 cubed over 3 plus 8 over 3. And believe it or not, that's the answer. Now you can go get the decimals that no one cares for, but that would be the answer. Too easy, huh? Crank the heat. How about we change the cylindrical integral into our rectangular integral? Sorry, change rectangular integral into cylindrical integral, so it's easy to integrate. You see, when you have, let's talk about problem number 20. When you have a triple integral from -4 to 4, then another integral that goes from negative root 16 minus x squared to positive root 16 minus x squared. And then the third integral that goes from square root of x squared plus y squared to 4. dz, dy, dx. Well, dz integral is easy, right? But the problem is that when you solve the dz integral, you get 4 minus this square root. And then it's time to integrate in respect to y. There is no y in front of this to use u sub. So what's your only option? Trig sub, exactly. Very good, trig sub. So x is going to be a constant, right? And you do the trig sub on y squared. And then after 25 minutes, when you're done with all of that stuff, you'll have a horrible thing there with these things plugged as a limit to compute. So now your expression is 3 pages long. And then you have to figure out how to integrate that, which you will not. Okay? Because I have made that mistake as a student. Right? And then, yeah, life doesn't work past that point. So what do we do instead? Instead, we understand the basics of triple integration. Outer two integrals, right? The first two. Outer two integrals, guys, I have to say outer two because dx, dy belongs to these. They come in pairs, all right? So outer two integrals are your domain. If you're able to draw the domain looking at the limits, hey, right? You should be able to transform this into a cylindrical integral at that point, right? And then clearly just change this to r squared and you're done. So that's exactly what we are going to do. I'm going to look at the outer two integrals and pick off the domain. And then once I have that, move along with stuff. So now I am noticing that on the middle integral, I have that the two functions that are presented to me, and I told you, look there first, y equal negative 16 minus x squared and y equal positive 16 minus x squared. What is this? Y squared equals 16 minus x squared, which is x squared plus y squared equals 16. What is it? It is a circle of radius 4. Very good. So two of these guys give you the circle of radius 4. Four, 4, negative 4, and negative 4. You have your domain. Now, you have to be very careful how you read this domain. So let's do what if. And let me use Coord to type some stuff. All right, ready? First off, we have this part of the circle and this part of the circle. The negative square root is the bottom line, bottom half of the circle. The positive square root is the top. Bueno? Good. Now, negative 4 to 4 on dx, could that be 0 to 4? Right? 0 to 4 would be just right half. Negative 4 to 0 would be left half. Negative 4 to positive 4 is the whole thing. Why? Because dx. What is dx? dx is this guy, right? That guy goes from negative 4 to positive 4. You're taking the entire circle, right? So now, if these two are zeros, what do I get to shade? How much of the circle I get to shade? Just the first quadrant. Very good. That's that. 0 and 0. Look. This kills the negative part of the circle, right? This being 0. And this being 0 kills the negative 4, so you start from here. So what's in the common denominator, right? Everything below x-axis is gone, everything to the left of the y-axis is gone, so only first quadrant survives. I can have any of those combinations here. I can put 0 anywhere I want, and it's going to mess up this beautiful full picture. Now, obviously, that changes your domain for polar, right? Because if I only have the first quadrant, your R is 0 to 4 for all of them, right? But what changes? Theta is changing. 0 to pi over 2, 0 to pi, 0 to 3 pi over 2, 0 to 2 pi for the whole thing. Or pi to 2 pi if I have a 0 up there. Right? If I have 0 up here. So please, don't go and change these things over here into polar stuff and try to fix it. It doesn't work that way. You have to use these integrals to create the domain, then you read the domain and you create the limits. The one that you fix directly is only this one. So this is where you get to swap in r squared, kills the root, so it's just r to 4. Bueno, right, that's done. But for the rest, you have to draw the domain from scratch, and then when you draw your domain, you are going to write your functions. So we have to be very careful, and actually I'm going to draw, after the problem is done, right, I'm going to draw some of those functions so we can know what's happening. So what is my integral now? It's a double integral, triple integral. We said it goes from r to 4, and we have now the z, r, dr, d theta, right? And your domain over here is the entire circle. So inside the inner integral, right, the middle one, is 0 to 4. That's our radius. And the outer integral is 0 to 2 pi, because the whole thing, right? And now you integrate this and you get a number. I'm not going to waste time, so here, boom. Just do it. All right? What I want to discuss is, again, the circle of radius 4, and thing that we had, what you just did verbally, I want to point out. So we're going to use some colors over here. I'm going to shade the top portion of the circle, and I'm going to say that that's the integral of, so it's just the upper portion. So I'm going from -4 to +4. And then I go from 0 to square root of 16 minus x squared. I still have the rest of the blah, 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 but that's what it corresponds to if you are looking at this. It's just the upper half. You notice that the 0 kills the bottom part. Yeah, r d theta. 0. Yeah, 0 to 2 pi for the theta. That's the outer integral, right? Or are you talking about the example I'm writing down there? Oh, no, I'm just talking about your input versus what you shade. I'm not, I'm not converting this into, well, actually I can. So I'll write the corresponding double integral over here. Would be, your radius is 0 to 4, and you go 0 to pi on the, okay, fine, there is a conversion there, sure. Another picture, another circle, 4, 4, -4, -4. You guys, you have to sit and study this. It's not going to be communicated to you in any way, shape, or form. You have to sit there, turn on your head, and stare at this until it's clear. I'm going to shade now this way over here. So when I shade this way, my input for that was 0 to 4, because there's nothing left of 0, and then I had a negative square root and a positive square root, because you see this part over here is the negative square root part. and this part over here is the positive square root part. So that's that, and that's that. So they both survive in that case. Okay? So that's my triple integral. This is 16 minus x squared and 16 minus x squared. Converts into, we have triple integral here. Again, 0 to 4. Radius doesn't change. Radius is always 0 to 4. It's a circle, okay? Now, what do I put for my limits on negative pi over 2 to positive pi over 2? Very good. You guys are awesome. What happened? I can't go from 3 pi over 2 to pi over 2. Right? I could, but then I have to use a negative, right? Because it would be going this way. So, if you're starting below x-axis, right, you'll be using negative pi over 2. From negative pi over 2 to positive pi over 2. It's still pi, right? And let's have another one. I want to shade just the quadrant. You tell me which quadrant to shade. Which quadrant should I shade? Quadrant 1, 2, 3, or 4? 3. Wow, you guys really wanted the third quadrant over there. Alright, fine. So, yeah, I think 3 people said 3 at the same time. Wow. Okay, so looking at the third quadrant, my x definitely goes from negative 4 to 0 because there is nothing on the right-hand side. And I have the negative square root of 16 minus x squared. And I have 0 for the top because there is nothing there. Again, not caring about the rest of this integral because I only use these two to create the domain. And I care what it converts to. 0 to 4, no surprises there. And what are my limits? Pi to 3 pi over 2. Nice. There we go. So I hope you're getting the hang of this. And these conversions are important. So don't switch inside. Now, what do you switch inside the integral? You switch the z. And then if you are looking for the fourth dimension, right, it would have the integrand inside. That also gets switched without doing these things. So this is only going to switch your, it's only going to switch your domain, right? So that's where it goes. Spherical integrals. Robotics, anyone? You did it? Good. Joints in robotics? Yes or no? Very rigid, right? Look at this. See that? Yeah, right? So the robot is going to do this. And that's it. And then you might be able to kind of give a little wiggle here and there. Look at this. Right? So now we're going to take a look at this particular motion and we're going to do it in spherical coordinates. And you can figure out the mechanics of that. Awesome, right? Get Boston Dynamics. So those videos in Boston Dynamics? Alright? It's going to be law enforcement soon. No, seriously. Yeah, why not? We better. So now, what do we have? For cylindrical coordinates, for spherical coordinates, you are going to have your good old origin, and you are going to draw the radius, r, and then you are going to have in xy plane, you are going to have your polar coordinates. So there's your r theta, right? It does this. So now I can't really do the full 2 pi, right? But you have to understand that you are starting to draw from 0 in x-axis. You draw the radius, so whatever this is, radius is 3. And then you swing that pi over 2, or pi, or 3 pi over 2, and 2 pi for the full circle, right? Same as cylindrical. It has one more angle for spherical, and that's this one. So it measures off of z-axis. Phi is measured off of z-axis back. So now let's see the way to draw the sphere in spherical coordinates. It's a joke. What you do is you decide your radius, there it is, and then what you do is you swing around to get the 2 pi disk. So now what do you have? You have a pancake, okay? It's round. And what do I need to do? I need to take that pancake and just rotate that pancake pi. What is going to happen when you take a pancake that is round and you rotate it pi? It's going to spike the sphere. Now, what do I get with the phi angle? If the phi angle starts at z-axis, all I need to do is to rotate from z to negative z, pi. And then the whole shape will just rotate. The pancake will flip, tracing the circle. One half of the pancake will draw the upper hemisphere of the circle, and the other part of the right, you see this? So this is one side, this is the other side, and it's like, just flip it like this. You see that this part draws the upper part of the ball, and this part draws the bottom part of the ball at the same time. So you're not rotating that one 2 pi. You are rotating only pi from this position to that position. Just like when you're flipping, when you I don't know, making mistake, right? That's pi. You just created a sphere. Right? So that's the way these coordinates work. So you are going to draw the radius, swing it for some angle, and then from the top drop it, and that shows the location. So our spherical coordinates are going to operate in a sphere. In this sphere, I have the origin that has your x, y, and z intersecting at 0, 0, 0. What I am going to do is I am going to draw the radius. Now, a radius is called a rho for whatever reason, right? It's been radius for years, r, right? And now it's rho. So enjoy that. I'm going to draw a radius rho along x-axis. I'm going to swing that theta, and then there is going to be another angle phi. That is the angle that it's measured off of the z-axis. You guys remember bearings from all the way in your pre-calc 2 class, when the bearings were measured off of the north?
Yeah.
You remember that? So this was 30 degrees, and then this is east. So you would say north 30 degrees east. You measured the angle off of the north, or you measured the angle off of the south, like this. So this is, let's say, 20 degrees. So you would be south 20 degrees west, because this is west on this side. You remember? Well, if you don't remember that, well, there you go. Now it's the same idea. This z-axis is becoming your north, right? Which is what the North Pole is, on the top of the z, right? And then you measure it off of that one. So you can reach any location. These coordinates are not friendly. We do not have a set of conversion formulas for this, because it's situational. You get to use whatever magic you have to use to do the conversion. You will have to draw the inner triangles. You will have to figure out inner trig, right? Because there is no conversion. Now, clearly, x and y domain going into polar, yeah. But the angle phi, that's going to depend on the situation, on what you're converting. So if you scroll through the book and try to find, I'm going to actually look for it now and display it. Where they explain there you go. Here's your conversion. Transformation between spherical and rectangular. What does it say? It says good luck. Right? That's what it says. So use trigonometry to find theta and, right? Because it depends on where they are. It depends on the quadrant, the sign, plus and minus and all of that kind of stuff. So if you're interested in these things, you will sit down and, right? Because eventually you have to program these kind of things. Right? You want to work with robots? Yeah. Because you have to have exactly where it's going to pick up things. If you want the robot to operate as well, right? You can have all the horsepower you want in that thing, but if you can't grab the object, right? And I can, because I have all that mobility, and if you can't program it in, you have to be able to program these equations in, right? This one, you're never going to use. So I'm not going to ask anyone to memorize any of this stuff. Clearly, you all know equation for a sphere, otherwise get out, right? Because this is just a circle with added z. And I told you rho is the new radius, right? So you all know that equation. And then r is the square root of these three. And that will pop up for us. But we won't have to use any of the other stuff. So it's nice to have it as a reference, right? And we only need to suffer with problems to, again, set up. Now these puppies are trickier because of phi. You are not used to it. You just remember how many times you messed up on your trig when you had bearings. Because you want to measure everything. You go 3.5 months in a class measuring all of your angles from x, right? And then all of a sudden you're measuring from y, right? Of course you're going to mess up. So now we have the same situation, but it's worse because all of your thetas are measured from x out and all of your phi's are measured from z, right? So now you have to really stop and think. But here's the diagram, right? The one that I try to draw, where you swing the radius on x, swing that around, and then drop the angle from z, and then that's your point, r phi theta. So the point that I have over here is r phi theta. I mean rho phi theta. So rho phi theta would be the spherical coordinates. Now, as I mentioned earlier, to draw, not to draw, to trace, build, construct sphere, to make, to make sphere, use not we, I. Can't we? The button is barely we. It's political correctness. Right? You just want to be nice. And now, you see what you did? You just ruined it, right? Alright. So, to make sphere use rho, right? And then we go, so rho equals, I don't know, some value. And then theta is going to be between 0 and 2 pi. And then so all of that gives us a flat disk. And now use phi, that it's going to be between 0 and pi to flip the disk. And that will give us what we need. So now that we understand these things, let's go and look at our volumes. Now, I don't know what would I call representative pieces here. Remember how I said representative French fry, representative pizza slice, representative rectangle? These guys, steak, but not the steak, the food steak, the steak, like the wooden steak for vampires, right? So maybe a steak, because it has a spike, right? And it's a pyramid, goes out, but then at the end is round, because it's a part of the sphere. Okay? So it goes out as a pyramid, it ends at a spike at the origin, and it goes out and it's rounded. Toothpick? I still like my steak better, because toothpick usually has 2 spikes on the ends.
Yeah.
It's never rounded nicely on the... But okay. I mean, we can use half of a toothpick, as long as you, right, smooth it out. So next time you have a toothpick at a restaurant, bring some sandpaper, make it smooth. It's like, here it is, right? This is the representative or toothpick piece for a spherical integration, which is a conversation starter. I mean, right? No? There's just so much that you can explain to the person that's clueless about these things. Come on. Yeah, I went to a party on Sunday, and you take a kid, right? Just don't have them, okay? You take a kid to a party, and you're happy that kid is happy and running around and playing with the friends. The problem is that you have to interact with others who brought their kids. And at one point I was like, if one more person tells me about the weather or asks me what I do, you know, like, and then I've been thinking about this like yesterday, and I said, well, I have a perfect way to counter this. What do you do? Or, let me show you. Let's just tackle spherical coordinates, okay? Let's tackle spherical coordinates, and then we'll transition into differential equations, right? Laplace and stuff like that, let's say. And after like 3 hours of them pulling their hair out, I would just say, and that's what I do. So yeah. It's like that, and when someone buys me a candle as a gift, I promise you, if you ever buy me a candle as a gift, I will make you eat it. Yeah, just don't get me anything, please. Like, I need nothing. All right. A candle, like really? First, every single one smells bad, it makes my head hurt. And the other one is like, why? I don't run a cult at home that I need a candle and then summon spirits and things. No. But it smells well. Really? Oh, it burns your house down, along with your pets and everyone else. So yeah. Anyway, so let's talk about the volume. Yeah, I'm not a cheerful guy. I'm sorry, right? So You know what's a good gift for me? A chocolate mousse cake, right? That's a good gift. I'm gonna like you, right? A candle. That's the reason why I'm fat. Can't eat candles. So, I'm serious. Well, you don't know me well, so. Anyway, triple integral. So let's put the formula down and take a look. So triple integral over the region D, and now the function that you might have to put inside will be in terms of rho and phi and theta, dv. So it's a four-dimensional entity as always, and then if you have this f as 1, it computes the volume. The most general case that we deal with is going to be the alpha and, well, let me just do the f, and then I don't have room for all, rho, phi, theta, there we go, on a pile right there somehow. We have a rho square sine phi, d rho, d phi, d theta. And I am going to actually over here specify the string. That's what I call it, the string. Rho square sine phi d rho d phi d theta. This is what you guys. This is what you're memorizing as a unit. That's a unit right there. All right. So we have that. Of course, I'm going to hate something that this book doesn't, and they use alpha and beta for angles on theta, and then they use A and B as angles for phi. No, just use other Greek letters like gamma and delta or something. So, I mean, I will stick with the book, but I hate it. So we need to make sure that, you know, that's there. And then the functions, obviously, right? G and H. That are there. Now, I actually want to write the volume integral, so we are all clear that the volume is the triple integral. Alpha to beta, here goes A and B, yeah, okay, fine. Of just rho squared sine phi d rho d phi d theta with these functions over here. Because generally we look for generally we are looking for the volume in these pieces. What's the most vanilla problem I can do? Clearly the proof for the formula of the volume equation for the sphere. What is the formula for volume of a sphere? 4/3 pi r cubed. Very good. 4/3 pi r cubed. When I'm done with this proof, it better be that as the answer. Otherwise, we broke mathematics and we can wrap it up and never show up again. Right? So, what is the volume of the sphere? This is a good honors question, if any of those students were here. Like none of them. So what do we say to create the integral for a sphere? Now, first, rho squared sine phi d rho d phi d theta. That's the string. You are memorizing this as a unit, right? You're memorizing that as a unit. All right. What did I say for theta? Theta has to go from 0 to 2 pi because it's creating the disk on the xy plane. What did I say for rho? Rho is the radius, so that's going to go from 0 to whatever the radius is. I'll just keep it as capital R. No, actually I can put a lowercase r, because it's rho. And what did I say for phi? 0 to pi, very good. 0 to pi because 1/2 will draw, one half will create one hemisphere and the other half of the disk, right? So you don't need 2 pi there. We just integrate this thing, right? So we are integrating first rho. Well, you have to integrate rho squared, which creates rho cubed. So the outer integrals stay 0 to 2 pi, 0 to pi. Rho cubed over 3 sine phi computed from 0 to r d phi d theta. Plug in r, and you already see that you are getting some stuff that is familiar and it's moving in the right direction. You are getting your r cubed over 3 sine phi d phi d theta. The next step is to integrate phi. Well, r cubed over 3 is a constant, so you can just copy that one, r cubed over 3. And the integral of sine phi is negative cosine phi from 0 to pi. Very good, very good. So that's 0 to 2 pi, r cubed 3. Now, cosine of pi, so you have a negative of negative 1 minus cosine of 0. So, another negative 1, right? Yeah, you have the minus from the formula for calculating and minus from cosine. Over here, you just have a minus from cosine and minus from the answer of the cosine. So, yeah. Yeah, it's going to be 2. And then I have d theta. So now I'm computing this, and I get 2. So the whole thing over here is 0 to 2 pi of 2r cubed over 3 d theta. So that's 2r cubed over 3, that's a constant, times theta, that's computed 0 to 2 pi. And when you plug in 2 pi, there's your 4 pi over 3 r cubed. Which means we did not break anything. We got the formula. Next time when someone asks you why, please, by all means, show them why. And since we didn't break anything in math, there will be another class on Monday, and we are going to learn how to, we'll try to finish off the chapter on Monday. We're going to learn on Monday center of mass, right? So we'll see why in martial arts, right, you don't want to stand tall like this, because on a tippy toe, right, when you're done, right, you want to go down. Center of mass. Why is it harder to flip Tesla than a minivan? Right? And think of that. Center of mass for Tesla is where? On the floor. There is just a battery on the bottom. There's no engine. That car has nothing. It's impossible to flip that car. It's impossible to flip it. No matter what you do, you can't flip Tesla. But, take anything else? What? Oh, take challenge accepted? Yeah, take the forklift, sure, right? But, I mean, driving it, right? But take any of those, Rocky Mountains. Right, if you take the first curve, little bump, that's it. So, there you go. That's going to be central mass next time. Well, no, we'll do a few more examples of this, obviously, and then we'll push.